This video is for topic 7.9, Introduction to Le Chatelier's Principle. The objective for this topic is to identify the response of a system at equilibrium to an external stress using Le Chatelier's principle. So let's talk about what this principle means. Any change in any of the factors that determine equilibrium conditions, so we're talking about temperature, we're talking about amounts, pressure, so any of the things that factor into determining equilibrium, any changes in those will cause the system to change in such a manner as to reduce or counteract the effect of the change. So the idea of equilibrium is that it always wants to go back to that steady state, that rate forward equals rate reverse. So if you make a change to any of the things that are going to affect either the reactants or the products, the reaction is then going to proceed in the direction to counter that change, so that equilibrium is reestablished. Now, we can manipulate certain changes so that we can observe how equilibrium is changing. So we can do this with pH, we can do this with temperature, we can do this by observing color. So there are a lot of different things that we can do that we can visually see that equilibrium is shifting. So let's talk about an example. So in this one, we have a 1 liter flask with butane at 0.005 molar and isobutane at 0.0125 molar. And it's in equilibrium, okay? And the equilibrium constant is 2.5. Okay, so we add then, so we have these two amounts in our 1 liter flask, and we add additional butane to the flask. Okay, so we've added additional reactants. What's going to happen? Well, if we have additional reactants, but we need to maintain equilibrium, we're going to shift and make more products because we need to counter that change. So if we have additional reactant, we're going to make more product. So if you think about it as the ratio, in order to maintain that K, that equilibrium constant, it is a constant, so it needs to go back to that same number. If we have a greater denominator, we need a greater numerator to be able to counter it, to come back to that equilibrium. So we would say that the equilibrium shifts to the right, or it shifts to the products, so we create more isobutane to counter the additional butane that was added to the system. Let's look at a different example. So we have an equilibrium here of NO2 gas in equilibrium with N2O4 gas. So our equilibrium expression would be N2O4 over NO2 squared because it has a 2 coefficient. And at 298 Kelvin, this is so roughly a little bit warmer than room temperature. This equilibrium constant is 170. Okay, so we want to know what's going to happen if the volume of the flask holding both gases is suddenly cut in half. Okay, so we have to go back to what we know about gases. If volume goes up, the pressures, or if volume goes down, because it's cut in half, so it's half the size. So if volume goes down, my pressure is going to go up. So to counter that pressure, I need to shift to the side that has the fewer number of gas particles, which would be to the products. Because on the reactant side, we have 2 gas particles, 2 NO2s, to every 1 N2O4. So to counter that increase in pressure, we need to shift to fewer gas particles, because fewer gas particles will then lower the pressure, and it will come back to our equilibrium. So it's going to shift to the right. What happens if you increase the volume by 5? So this is the opposite. So the volume is going up, and so that means our pressure is going to go down. So then to reestablish equilibrium, we're going to shift to produce more particles, because more particles is going to bring the pressure back up. So it's going to shift in this case to the left, or to the reactants, because that's the side with more particles. We have 2 NO2s on our reactants compared to 1 N2O4 on our products. Okay, so let's talk about temperature. So same reaction. But this time I'm also telling you that the enthalpy of reaction is negative 57.1 kilojoules per mole of reaction. So that tells us that this is an exothermic reaction, or we can treat heat as if it's a product because we are producing heat that's then going to leave our system. So if heat is a product, we can imagine writing in plus heat as one of the products next to N2O4. We want to know what would happen if we lower the temperature of the system. Okay, so this means that we are going to decrease the amount of energy, decrease the heat. So if we remove heat, if we treat heat as one of our products, we're removing heat from the system, which means to reestablish that equilibrium, our equilibrium is going to shift to the side where that heat was removed. So it's going to shift to the right, it's going to shift to the products because heat is considered a product in this reaction because it is an exothermic. So here we have a summary table that describes each disturbance or stress or change to the system that we could make and what that change is, what's going to happen in order to return to equilibrium. And so then that we're going to look at the shift in equilibrium and the overall effect on K, the overall effect on the temperature. So the only thing that we can change is going to, that's going to affect our K or our equilibrium constant is temperature. So equilibrium constants are temperature dependent. So changing the temperature will change the equilibrium constant. A rise in temperature means you're adding more energy to the system. So it's going to be consumed by the system. So it's going to shift in the endothermic direction. So if it's an exothermic reaction, it's going to shift opposite. If it's an endothermic reaction, it's going to shift that way. A drop in temperature means that the system is going to generate more energy in order to account for the drop in temperature. So the reaction will then shift into the exothermic direction. This also has an effect on the equilibrium constant. The other changes, addition of reactant or product, or change in volume or pressure, does not have an effect on our equilibrium constant. It will change the equilibrium, the reaction will shift, but the constant itself will stay the same. So if we add reactant, there's more reactant to be consumed, so we're going to produce more product. So it's going to shift to the product side. Addition of product means there's more product to be consumed in the reverse reaction, so more reactant is going to be produced. So if more product is produced, it's shifting to the right. If more reactant is produced, it's shifting to the left. A decrease in volume and therefore an increase in pressure means that the system needs to decrease the pressure to return to equilibrium. So we need to reduce the total amount of gas particles. So it's going to shift in the direction of the reaction with the fewer number of gas particles. Likewise, an increase in volume is going to result in a decrease in pressure, which means to come back to equilibrium, the pressure needs to go back up, which means that in order for the pressure to increase, the equilibrium will shift in the direction of the side that has more total number of gas particles. So this slide just gives us a summary of the types of stresses or disturbances we can put on a system and what that's going to do to the equilibrium.